All right, so let me go over the problem in the problem sheet. And meanwhile, you may ask, other related things, if there's anything you don't understand. So, so this is homework sheet. Five. First question is the following. So we have a linear operator, and we are given that A is diagonalizable. We are asked to do the following. So that the determinant of this operator is just the product of the eigenvalues, right? Lambda 1 up to lambda lambda I are value of A. All right, how can we show this? Well, an operator is diagonalizable means there is a basis of the vector space consisting of eigenvectors, right? So this A is diagonalizable. There is a basis. Let's say beta v1 up to vn of E consisting of eigen vectors of A head. So this means what? These are eigenvectors. So each vector is mapped to what? To a scalar multiple of this vector, right? Lambda I, I from 1 to. And supposing that dimension of this V is n, so let's assume that dimension of V is just n, okay? N dimensional vector space for some lambda I in K. So we have a basis like this, right? This is the definition of the diagonalizable. And we are asked to show that in this case, determinant of A is just the product of these lambdas. Here I don't claim, for example, these lambdas are different. Maybe some of them are the same. Okay, I have n eigenvectors, and eigenvector means that A, if A had keep this right, you get a multiple of that. Okay, now how can we determine the determinant? Well, for the determinant, we have to look at the power. We look at a head and power applied to the vector, which is just the this exterior form of this vectors, right? And how does this action was defined? It was so a and power means you hit each vector by A, and then you take the exterior power. So A hit V1, which A hits V2, which A hit Vn. But by definition, I mean, by the choice of these elements, there are eigenvectors, right? Vi's are eigenvectors, and A hit Vi is just lambda and Vi. So this thing is just lambda 1 times V1 with lambda 2 times V2 with lambda n times Vn. Well, in wedge product, we know that we can just take constants and slide them wherever you want. So I can just take this constant here, this constant here, and so on. So this is just lambda 1 times lambda 2 times lambda n times V1 wedge V2 wedge Vn. So what we see is that a head takes this guy and sends it to a multiple of that, and that multiple is just this number. Therefore, this is the determinant, right? This is the definition of determinant. So hence, the determinant of a head is just lambda 1, lambda 2, lambda. Yani volüm elemanını kaç katına getiriyor? This vector is just mapped to that vector times a number. Whatever this number is, it is defined to be the determinant of this linear operator. Therefore, it is. Tamam mı? Doğru. Olur. Okay, so your friend suggests another method. Let me just explain. Second solution. Well, actually, you don't even need that, but suppose you have some basis, let's say beta prime, and in that basis, the matrix representation of a head. So in this is the matrix A, okay? Suppose it is this one, but I know that there is a basis consisting of eigenvectors, and in that basis, if you write a head in this basis, then we know that this is just a diagonal matrix because this is just lambda 1, lambda n, right? Because each element Vi is just mapped to lambda I times Vi. Therefore, this is the matrix representation. And we have a relation between these two. What is the relation? D or okay. A, let's say, this was the matrix representation of a head from D beta prime to beta prime. And we know that it can be obtained like this. Here I write identity, and here I write A, and here I have beta to beta, and then here we have what? We have beta prime to beta, beta to beta prime. So if this is the matrix P, this is just what? The diagonal matrix D, and this is just the inverse matrix P prime, P inverse. In this case, what would be the determinant of A, the matrix A? A is just, it can be any matrix, not necessarily diagonal. Okay, it's just a matrix. But it is diagonalizable, therefore, in some cases, it is this diagonal matrix. And determinant of A as a matrix is just the determinant of what? A is just P, D, P inverse. But what we know is from the properties of determinant, we know this. Determinant of a product of two matrices, right? can be written like this. You can just switch the term components of the product, right? Determinant of A times B is the same as determinant of B times A. Therefore, for this one, I can write the following: determinant of A, which is determinant of P, D, P inverse. I can do the following. Consider this like A and this one is B. So I have this times this, right? Two matrices multiplied. I can switch the order. So I can first write P inverse and then P. Okay. Switching this matrix and this matrix. But what we see is that P and P inverse are inverse of each other, so it's identity. Therefore, this is just determinant of D. Okay, and D is just this matrix, everything is 0 except the diagonal ones. What is the determinant? The determinant of D is just lambda 1, lambda 2, lambda. Seni sorduğun buydu değil mi? Tamam. O zaman determinant yok. Ha. Ne yapabilir misin? Yok, o da yer değiştiremezsin. O zaman çünkü o da kare hissediyorsun. Olmaması lazım. Çünkü birisinin determinantı her zaman 0, diğeri non-zero olur. So your friend asked the following remark. Suppose A is a, let's say, 3 by 5 matrix. And B is 5 by 3 matrix. So A times B is what? 3 by 3 matrix, right? I can talk about determinant. And B times A is 5 by 5 matrix. So both of them has determinants. Can we say that determinant of A times B is the same as determinant of B times A? Is this true? Right? Güzel bir sınav sorusu bu. Nedir cevabınız? Böyle bir şey doğru olsaydı öğretirdik, değil mi? This is not true. One of these determinants is always 0. And the other can be non-zero. Therefore, in general, this is not true. But to prove that it is not true, all you need is to give a counter example, right? 3. So just answer is no. And you just need to find a counter example. Let's say
3 çarpı 5 çok büyük oldu. 2 çarpı 3 falan.
1 çarpı 2 de yapabiliriz. Değil mi? Yok, olur mu? 1 çarpı 2, 2 çarpı 1. Olur tabii. Öyle yapalım. A'yı mesela 1 çarpı 2. 1'e 2. B'de 2 çarpı 1. Eksi 2'ye 3 olsun. Tamam mı? A times B nedir? A times B 2 eksi 2 bu sadece 4. B times A okay. Eksi 2 ile bunu çarpıyorum. Eksi 2 eksi 4. 3 ile Bunları çarpıyorum değil mi? Öyle bir şey. Eksi 2 ile çarptım. 3'e 6 mı? Dikkat ederseniz bu ikisi lineer bağımlı. Right? So, what is the determinant of B times A? This is 0, but determinant of A times B, one by one matrix determinant is just this empty, this 4. And these are not 2.
Bir tanesi sıfır çıkartıyor.
Evet.
Var mı?
Evet. Bir tanesi her zaman 0. Neden? Evet.
Yani bu her zaman geçerli olan bir şey değil. Bir sistem var.
Lineer bağımlı oluyor.
Efendim?
Lineer zaten lineer bağımlı oluyor. Yani tabii çarpı 5 ve çarpı 3 de bilirsek.
Evet. Bir tanesi hep 0. Anladın mı bunu? Başka anlayan var mı? Bir tanesi hep 0.
Öyle.
Yani eğer tutmuyorsa şeyler. So if the sizes are not the same, I mean if they are not square matrices, then but if you can multiply both of them, I mean this way and this way, one of them will have always determinant 0. The reason is the following. Burada olduğu gibi yani aslında B times A. So you multiply this entry with this row, you get this row, and then you multiply the same row with another number. But you see, both of them are just multiples of this row. Okay, therefore they are linearly dependent. And the general case is similar. Yani nasıl olacak? Şimdi B çarpı A dedik. B çarpı A. So B times A. B times A. So I take B çarpı A olunca hangisinin size büyük? Şöyle diyeyim önce bunun A'nın kanunları C1, C2 yok R1 rollarına bakayım. When you multiply with B, no, kanunlarına bakmam lazım. So if I write this as columns, first column, second column, and column. So here A is okay, şöyle diyeyim. A is n by n matrix. B is n by n matrix. And hangisi büyüktü? Hangisi büyüktü? M mi büyüktü? Yok. M büyüktüsün. And bigger than n. Yani şuradaki gibi. Bu 1 çarpı 2. 2 çarpı 1. 2 birden büyük. Tamam. So, I look at the following. B times claims this determinant of B times A is always zero. Okay, is always zero. You can multiply them, but you get it has zero determinant. The reason is the following. What is B times A? This is B times A. A is an n by n matrix. So it has columns. And how many columns? It has n columns, right? So we have C1, C2, Cn, right? This is an n by n matrix. And each Ci is a column matrix. And what kind of matrix is this? This is in R or K M tane şey var değil mi? M çarpı 1. Yani M tane entry'si olan bir column matrix. Okay. When you multiply with this, what you get? B is multiplied with the first column. So the first column of the product is just BC1. This is the first column. BC2 is the second column. BCN is the nth column. This is now what kind of matrix? This is an M by N matrix. Evet. M by N matrix. Tamam mı? Büyük olan ne çarpı? Büyük olan ne? Tamam. Ne çarpı? Evet. Değil mi? Şimdi iddia şu. Bunlar lineer bağımlı. Neden lineer bağımlı? So determinant of this is just determinant of this and determinant of an n by n matrix. These are the columns, n columns. It is 0 because these columns are linearly dependent. Why is that? Well, you see, the columns, the n many columns, değil mi? N tane var. Many columns are elements of which vector space? K m times 1, which has dimension bunun dimension ne? M. Ama I have n many of them and n is larger than n. So these columns cannot be linearly independent. Yani elimde R3'te 5 tane vektör var. Onlar lineer bağımsız olamazlar. Değil mi? R3'te en fazla 3 tane vektör lineer bağımlı olur. Dördüncüyü koyduğumuz anda patlar. Dolayısıyla bunlar da lineer bağımlı. Hence BC1, BC2, BCN are linearly dependent. But I have a matrix whose rows are linearly dependent. Therefore, its determinant is 0.
The n many columns are the elements of n times n or n times 1.
Each column is an element of this matrix space.
But p times ci is an element of k n times 1, right?
Ha, pardon. Haklısın. Orada yanlış yaptım. Okay. These are not in this. They are in şöyle. Okay. Şöyle demem lazım. Şu kalınlar lineer. Okay. So I still claim that these are linearly dependent, but the reason is that these are linearly dependent, right? C1, C2, Cn are in K m times 1, and since n is larger than m, they are linearly dependent.
In which I mean dimension they are linearly dependent.
Sorry?
In which vector space they are?
Two.
But n is greater than n.
So yani K üzeri 3'te 5 tane vektörüm var. Vektör sayısı boyuttan fazla.
But in the beginning, I choose the A. I can choose A like its columns not linearly dependent, right? This T1.
You cannot do that. A'nın kalınlarını lineer bağımsız seçebiliyor musun? Sıkıntı orada. Evet. So here we have n many columns, but they're in a vector space of dimension km. So, for example, I have C1, C2, C5 in R3. They are necessarily linearly dependent. Okay? Well, since they are linearly dependent, this means what? This means so there are constants, let's say ne diyelim? C'leri kullanmak istemiyorum. Mu1, mu n, not all zero. So that mu1 C1, mu n Cn is just zero. But if you just hit this guy with the matrix P, şuraya yazayım. Right, take this and hit this guy with B. B times mu C1, mu1, mu n Cn is equal to B times 0. Well, this is just mu1 B C1, mu n B Cn, B times 0 is still 0. And I know that at least one of these mu i's is not 0 because they are not all 0. So some of these mu i's is not 0. But this means that these vectors are linearly dependent. Right, so this is like PC1, PC2, PC are linearly dependent. And since they are linearly dependent, so the columns of this matrix are linearly dependent, therefore the determinant is 0. So this implies determinant of two times is 0. Nasıl?
Paralelogramın dimension'ı düştüğü için.
Evet, tabii ki olabilir. Tamam mı? Neyse, bunu burada çözdüğüme göre sınavda soramam artık.
Hocam kaldırabilirim.
Şunu. Yani?
Zaten bu.
Yok, bu şey olarak kolay bir soru değil ama efendim? Evet, size bir şeyler var. Önce 3'ü yapayım, o daha yumuşak bir soru. Gecenin ilerleyen saatleri geçiyor. Okay. Bunu yaptınız herhalde değil mi? 1, 3, 5, 3, 3, 2, 4 2 eksi 2 4 0 0 0 0 4 eksi 1 7 eksi 2 3 eksi 1. D şıkkından başlayayım. So in part D, we are asked to solve the following equation. And x equals b, where b is this. Minus 2, 3, minus 1, transpose. How can we solve this? Well, it is not a square matrix, so the best way is to use Gaussian elimination, right? So let's do that. I will write this matrix 1, 3, minus 2, 0, 4, minus 2, and then that is equal to minus 2, right? The right side of this the equation, minus 2, 3, and minus 1. 3, minus 2, 4, 0, minus 1, 3. 5, 4, 0, 0, 7, and minus 1. Okay, now to solve this, what can we do? Well, first, I can just multiply the first row by minus 3 and add to the second row. So second row is replaced by second row plus 3 times, no, minus 3 times the first row. So what is the result? What is the result? Şunu yazalım. 1, 3, eksi 2, 0, 4, eksi 2, eksi 2, 0, eksi 3 ile çarpıp topluyorum, değil mi? Eksi 11, eksi 3 ile çarpıp topluyorum. 10, 0, eksi 3 ile çarpıp eksi 13. Eksi 3 ile çarpıyorum. 6, 9. Eksi 3 ile çarpıyorum. O da 9 olur. Tamam. Bunu da eksi 5 ile çarpıp toplayayım. So we multiply with minus 5 and add to the third row. Yani bir bunu yapıyorum, bir de üçüncüyü de R3 eksi 5 tane R1. Burası 0. Eksi 5 ile çarptım. Eksi 15, eksi 11. Eksi 5 ile çarptık 10. Eksi 5 ile çarptık. Eksi 5 ile çarptım. Eksi 20. Eksi 13. Eksi 5 ile çarptık. 19. Eksi 5 ile çarptık. 19. So we see that the last two rows are the same. Now I'll do another operation. Multiply the, okay, second row, no, third row is just third row minus the second row. Well, 1, 3, minus 2, 0, 4, minus 2, minus 2, 0, minus 11, 10, 0, minus 13, 9, and 9, and this is just 0, 0, 0, 0, 0, and 0. You may stop here, or you may just continue, divide this with minus 11, and then kill this guy. You can do that, but actually, for our purposes, you may stop at this point. It is not the row reduced echelon form. I mean, this is not the row reduced echelon form. To obtain the row reduced echelon form, I should make this one and kill this guy. Okay. But you know, to write down the solution space, I can stop here. So what we see is the following. If these are my variables, let's say, so this is my variable x1, x2, x3, x4, x5, and x6, right? 6 variables. These are the dependent variables, right? Because it has rank 2, these are the dependent variables. These are the independent variables. So any solution is obtained by just giving arbitrary values to these guys. So we can just write down the solution as follows. Okay. İsterseniz gerçi şey yapalım mı? O ikisi. Evet, onu iki adım yapayım. İlk önce şunu bir bölelim. 0, 1, minus 10 over 11, 0, 13 over 11, and 9 over 11, with a minus sign, and eksi 11'e böldüm, eksi 9 bölü 11, 0, 0, 0, 0, 0, 0, 0. Sonra da bunu eksi 3 ile çarpıp buraya toplayacağım. 0. Eksi 3 ile çarpıp topluyorum. Eksi 3 ile çarparsak 30 bölü yani efendim eksi 2 artı 30 bölü 11 değil mi?
Hocam eksi
Efendim? Eksi 3 ile çarpıyorum. Özür dilerim. Tamam.
Artı.
8 bölü 11 artı.
Artı mı? Ha, eksi 3 ile çarptım. Artı. O halde ne oldu? 8 bölü 11 mi?
Evet.
Tamam. Sonra 0. Burası kolay. 4. Ne yapmıştık? Eksi 3 ile çarpıyorduk. Eksi 3 ile çarparsak eksi 3 ile çarpıyorum. Eksi 39 bölü 11. 44 bölü 44 eksi 5 mi? 5 bölü 11. Sonuncusu nedir? Eksi 2 5 bölü 11. Tamam. Burası 9 bölü o da aynı. Evet. Değil mi? İlk bir sahne olduğu gibi. 5 bölü 11. Tamam. Evet.
İşlemi yazabilir miyim?
Hangi işlemi?
Ben işlemi dedim.
Ha, hangi işlem? Evet. Şöyle ne yaptık? Pardon, ilk önce eksi 11 bölü 11, eksi 1 bölü 11, şuraya yazın işlemleri. Minus 1 over 11 R2, and then ne yaptık? R2'nin eksi 3 katını R1'e R1 ne veriyor? R1 artı eksi 3 tane R1. Ama önce bu sonra bu. Değil mi? Peki şimdi bir daha şey yapalım. So my variables x1, x2, x3, x4, x5, x6. These are the variables. These are three variables. So any solution can be written like this. Yani buradan aslında şunu yazıyoruz değil mi? X1 plus 8 over 11 x3 plus 0 times x4, I don't write it, and then 5 over 11 x5 plus 5 over 11 x6 equals 5 over 11. And here x2 minus 10 over 11 x3 plus 13 over 11 x5 minus 9 over 11 x6 equals minus 9 over 11. So buradan ne çıkar? Şimdi şunu yapabilirim. These are three variables. I can just take them to the other side. So solution is just, so x1 is just minus 8 over 11. If you want, I can just give parameters to this numbers. I mean, call them parameters. Let's say this is S1, this is S2, this is S3, and X6 is S4. So for three variables. So this is just S1, and then minus 5 over 11 S3, and then minus 5 over 11 S5 plus 5 over 11 S4. S4 yok. Şurası. Tamam. Özür dilerim. Tamam. X2 nedir? O da 10 over 11 S1 minus 13 over 11 S3 9 over 11 S4 and minus 9 over 11. Okay, now what is the solution then? Okay, x1, x2, x3, x4, x5, and x6. This is the solution, right? So what is this equal to? X1 is this. Let me go write it right now. X2 is this. X3 is just S1, S2, S3, and S4. And I can write it as follows. So there will be some S1 terms. S1 times what? S1 times, the first one is minus 8 over 11, and then 10 over 11, and then this is just 1, and then these are 0 because there is no S1 here, plus S2 times S2, there is no S2, right? So 0, 0, 0. Ha, evet, bir tane bir var. Nerede bir var? 0, 0, 0, şurada bir var. 0, 0. Evet, özür dilerim. S3 S. Ha, evet, orada da bir gariplik oldu, değil mi? Yok, daha yazalım. Bir dakika. S1 buradan ne geldi? Eksi 8 bölü 11. 10 bölü 11. Değil mi? X2'den, X3'ten 1, X4'ten 0, x5'ten 0, x6'dan 0. S2'ler S2 hiç yok, değil mi? Ha, evet, pardon, dördüncü de var. 0, 0, 0, 1, 0, 0. Tamam. S3 eksi 5 bölü 11, değil mi?
Eksi 13.
Eksi 13 bölü 11. Ondan sonra 0, değil mi? X3'te yok. Yok. X3'te yok. Şöyle. Tamam. S4
Eksi 11. Eksi 5 bölü 11. 9 bölü 11.
bir daha söyle.
Eksi
Eksi.
5 bölü
Aha.
9 bölü 11. Böyle 0. 0 en sonuncu 1.
Tamam. Bir de ne kaldı? En son 5 over 11 minus 9 over 11 and all the rest is 0, right? So this is the solution where S1, S2, S3, S4 are arbitrary real numbers. So my solution set is this, okay? There are 4 free variables, and this is the non-homogeneous part, right? This is the non-homogeneous part, and this is the set of all solutions.
Burası körü var.
Şurası, bunlar kernel'da. Tamam mı? Biraz uzun ama basit.
Yani.
Evet. So, first part was the row reduced echelon form of A. What is row reduced echelon form of A? Is this matrix, right? Row reduced echelon form of A is this one. You just forget part B, right? Row reduced echelon form of A is this one. You forget this part. So. Ne kadar bulabiliyorsun? Bak şimdi 2 tane bulduk. Burada artık 0 row var. Non-zero bir entry olsaydı, bunu bir yapmanın bir anlamı yok. Çünkü burada zaten var. 3. satırda şurada eleman olsaydı, o zaman onu bir yapıp bunları öldürdük. Ama burada bitti bu.
Renkli de onun base'ine göre.
Evet, rankı da işte 2 tane şey var. Matris'in rankı da 2. Şimdi C şıkkında şey soruyor. Yok, B şıkkında basis for the row space. So what is the basis for the row space? Well, in this row reduced echelon form, you just take the non-zero rows, they form a basis, right? So a basis for the row space of A is what? Is this one? You just take the non-zero row. 1, 0, 8 over 11, 0, 5 over 11, and 5 over 11. This is first vector. The second one is 0, 1, minus 10 over 11, 0, 13 over 11, and minus 9 over 11. Okay, so this is a basis. What about a basis for the column space, a basis for the column space is what? You look at the row radius echelon form, and then you decide which columns you will take. When you look at this one, what you have to do, you have to pick up two linearly independent columns. Of course, these are linearly independent. You can just take this two, or you may take this two, right? Actually, any two non-zero columns are linearly independent here. But for simplicity, I can just concentrate on the first two columns. But then I know that these are not the vectors of my column space. I have to go back to the original one. So this means that you may take first and second columns as your base. I come here and first and second columns. So I can just pick up these two as my basis of column space. So what are they? 1, 3, 5 and 3, eksi 2, 4. I could choose other columns, but just to be safe, right? I just choose this two because I am sure that these two columns are linearly independent. Tamam mı? Anlaşıldı mı? So applying row operations changes the column space, but doesn't change the dimension of the column space, and also you may keep track of the linearly independent vectors. So when you apply a rows operation, the columns which were linearly independent stays linearly independent. Why is that? Applying row operation means what? You just multiply columns by a matrix, right? If two columns are linearly dependent, when you multiply them with a matrix, they are still linearly dependent. Okay, so linearly dependent ones stays linearly dependent, and linearly independent ones stays linearly independent because the matrix you multiply is an elementary matrix, and they are invertible. Since they are invertible, they preserve linear dependence and independence. Okay. Row operation, applying the row operation, just multiplies these columns with the same matrix, elementary matrix. But that elementary matrix multiplication is an invertible operation. Therefore, it preserves linear dependence and independence. Linearly independent vectors stays linearly independent. Linearly dependent ones stays linearly dependent. Okay, that's why once these are linearly independent, I know that the first two columns are linearly independent. Tamam mı? Ara verelim mi? İyi, ara verelim bir 10 dakika.